All right. Moving along with electrophilic aromatic substitution. The last two videos I did looked at what happens in electrophilic aromatic substitution with one substituent on the aromatic ring. Well, what if you have two? So we have a methyl group here and we have a nitro group. We made this in that first monosubstituted electrophilic aromatic substitution video. So let's nitrate it again. So let's take nitrotoluene and treat it with nitric acid and sulfuric acid. And again, this is going to make NO2 plus, right? Okay, so what are we going to get? Now there's two positions, right? So the two positions ortho to methyl are identical, and the two positions ortho to nitro are identical. There's a line of symmetry here through the methyl and the nitro. And so our two choices are this. We can get that nitro to go ortho to the methyl, or we can get it to go ortho. I drew this in now, sorry. And you could probably work this reaction out already. Sterically, this one is better, right? The NO2 group's big, it's flat, takes up some space. Methyl's not quite as big, so having the NO2 there might be a little bit better. Two electron poor things right next to each other is going to be tough. And methyl's electron donating, so it's going to direct ortho and para. Well, para is blocked, so it's going to go ortho. Nitro is electron withdrawing. All right, so that's electron withdrawing. This one's electron donating. So the nitro is going to direct meta. So methyl and nitro agree that the second nitro should go there. So that's pretty quick, but I want to go through this and I want to state a rule. Okay, so I'm going to put up another reaction now and show and ask you to work that out. So the rule is this: if two groups direct to different positions, so let's chlorinate methoxymethylbenzene. What is that? I don't know. Methyl anisole, I guess. Anyway, if we chlorinate this thing, methoxy's a donator. Electron donating group. Methyl's a donator, right? So the methyl's going to donate or direct ortho. They're each going to direct para to each other, but para is blocked. So we can only substitute for H+. That's not completely always true, but for this class it is. The only thing we're going to be able to substitute is H+. We're not going to lose CH3+ or OCH3+. So the para positions are blocked. So methoxy will donate to its ortho positions. The methyl will donate to its ortho positions. So what do we get? Here are the two options, right? There's chlorine ortho to the methoxy. Chlorine ortho to the methyl. You might think you'd get both. They're both electron donating groups, so why not? Well, the answer is, right, the methoxy has lone pairs. All right, methoxy, even though you think oxygen's more electronegative, it's got a full lone pair it can donate to the ring. If you think about why a methyl group is donating, it's hyperconjugation. Some of you will have heard of this, some of you won't. You can look it up if you want. This, I think it's in chapter 8, 7. It's why tertiary carbocations are better than secondary and so on. Right. So the electrons that are being donated into the ring actually come from a bond, right? So electrons in a bond are going to be more stable than a lone pair. So they're both, while we have two electron donating groups, an oxygen substituent is going to be a strong electron donating group. The methyl is going to be a weak electron donating group. And so the product is going to be that one. All right? The methoxy is going to dominate this reaction. It's going to dominate the methyl group. The electronic effect of the oxygen, the OCH3 group, is going to be way stronger than the electronic effect of the methyl. And so that incoming nucleophile, or sorry, the incoming electrophile is going to go ortho to the stronger donor. All right, so this is really the rule. A lot of times, this two substituents will agree. And if that happens, then obviously that's where it goes. Sometimes they'll conflict. So if there are two substituents, two or more substituents, there could be three substituents here, and you'd have the stronger donor direct. So if you have a strong donor and an electron withdrawing group, like if this was a nitro or something, it would still go here, right? All you need to find the strongest electron donor on the ring, and that's going to tell you where the substituent goes. All right, one last thing to follow up. Here we've made dinitrotoluene. If we nitrate this again, we get this molecule. That is trinitrotoluene, better known as TNT. And so this is actually how TNT is made. You can get toluene from petroleum. Nitric acid and sulfuric acid are pretty easy to come by on an industrial scale. This first reaction goes pretty well. Let's see how I'm doing on time. You know what? That's long enough. I'll talk about this on the next video.